Welcome back to our learning video series for Phoenix LiDAR Systems. My name is Kory and I'm the Senior Geomatics Engineer here at Phoenix. It's my pleasure to walk you through the LiDARMill workflow from start to finish. In this video, we're going to cover how to create a new LiDARMill project, uploading mission and reference station files to a project, post-processing GNSS-aided inertial trajectories using a Navlab pipeline, generating high-accuracy georeferenced point clouds and other data products using a spatial fuser pipeline, and finally, viewing, analyzing, and sharing data through LiDARMill's integrated cloud viewer. Let's get started. To create a new project, click the Add New Project button within the Projects tab. A Project Details window will open. Give your project a name and a description. Click Next to proceed to the Project Reference Setup tab. The project CRS is one of the most important configurations within LiDARMill, as this coordinate reference system will be used for all process data outputs, as well as any uploaded files, including ground control point files. Click here to choose your project's coordinate reference system. Select a coordinate reference system that was previously used on another project by clicking here. Click Finish after selecting a CRS from a previous project, or alternatively, add a new coordinate reference system to be used for the project. If you wish to create a new project CRS, click here to move on to the CRS selection wizard. Begin by selecting an approximate location for your project by clicking on the map or searching within the search bar. If you do not have a preferred CRS, you can flip this switch to enable a generic coordinate reference system for your project. The selected project location determines which WGS84 UTM zone will be set for the project. If you have a preferred CRS, leave this switch disabled. Click Next when finished. Select a project datum and units. The Show Recommended Datum switch is enabled by default. All subsequent data imports and exports within this project will utilize the selected coordinate reference system. The selected project CRS will be applied to imported ground control points, post-process trajectory outputs, as well as all finalized point clouds and corresponding data product outputs. Click Next when finished. With the datum selected, you should now select the project's horizontal coordinate system and corresponding height type. When you select orthometric as the height type, you will need to select your desired geoid model and corresponding vertical coordinate system. Click Next when finished. The final step is to confirm or edit the project CRS name. The CRS configuration will be saved to your LiDARMill user profile under this name. This way, if you would like to utilize the CRS in the future, you will be able to select it from your profile's project CRS list. Click Finish to finalize your project CRS. Next, you can choose whether or not to import ground control to be used for data optimization and/or absolute accuracy analysis. If you do not have GCPs for the project, click the No GCPs button, and then click Next to continue to the Summary tab. If you do have GCPs for the project, click the GCP File button. To import ground control points, drag and drop the GCP file here, or click to import from Dropbox. Matching the proper column header to the corresponding data column in the file is the first step. Then select the proper row number under Index of First Data Row. The next step is to denote the type of surveyed point between control, checkpoint, and unused. Control points leverage GNSS data to adjust LiDAR and LiDAR-derived models to improve their absolute accuracy. Control points are not used to assess absolute accuracy of the process point cloud. Checkpoints are surveyed points with known coordinates that are used to validate the accuracy of the final point cloud. Unlike control points, checkpoints do not affect how the point cloud is processed in any way. All checkpoints are utilized to compute the absolute accuracy of the process point cloud. Unused points will be ignored during the processing. The final step is to review the map at the bottom of the window to verify the input survey control is properly georeferenced. Double-click on a GCP to zoom into its location on the map. The stated vertical offset is for quality control, to help ensure GCPs are in the correct location based on your specific project CRS. It's okay if they are off by a small amount, but tens of meters indicates an issue. Click Next when finished. Review the project details in Coordinate Reference System configuration under the Summary tab. Click Create Project to finalize project creation. With the project created, the next step is to upload mission data. In the Missions tab, click the red plus button to create a new mission. You can upload your project files from Dropbox or from a local drive. Begin by selecting the dataset type. Select Recon if you are processing data from a Recon series system. Otherwise, select the desired Spatial Explorer version. For systems other than the Recon series, once the Phoenix LiDAR project PLP file is uploaded, LiDARMill will recommend files to upload, files that are associated with the uploaded PLP, which could include navigation, LiDAR, and/or camera data. If you are only interested in post-processing a trajectory, upload only your nav and PLP files. In this video, we will be processing a Recon Systems data. Upload all data files from your Recon mission. Navigation data, LiDAR, and imagery are all stored within these files for the Recon series. Multiple missions can be uploaded to the same project and combined in order to produce a single calibrated point cloud. If you have multiple missions, continue to upload the rest of the mission data before moving on to the next step. When you create a multi-mission project, it is recommended to give each mission a unique and meaningful name. If you collected data using a static GNSS reference station during your mission, move on to the Reference Station tab to upload reference station data. With the mission data uploaded, the next step is to upload reference station data to be utilized for post-process kinematic trajectory processing. If a reference station is not uploaded, Navlab will default to the less accurate PPP trajectory post-processing. In the Reference Station tab, click the red plus button to create a new reference station artifact. Multiple reference station files can be uploaded simultaneously if they share the same position but differ in time. Upload files separately if the various reference station positions are not identical. Select the reference station antenna model used to collect static observations. A refined position will be computed at the antenna's reference point. During trajectory processing, Navlab will utilize the input antenna model to determine the accurate phase center position of your reference station antenna. Click Upload when finished. Once the reference station file is finished uploading, navigate to the Pipelines tab. After the Analyze Reference Station pipeline has finished successfully, navigate to the Refined Reference Station Position Reports by clicking on Analyze Reference Station and then click on the Job Runs tab where you can view the Opus and Trimble RTX reports. LiDARMill offers numerous data processing tools called pipelines. In this video, we will be using the Navlab pipeline to post-process the navigation data to refine your mission's trajectory. We will then use this refined trajectory within a spatial fuser pipeline in the creation of a point cloud and to derive other high-accuracy georeferenced data products. To begin processing your trajectory data, create a Navlab pipeline by navigating to the Pipelines tab. Under Select Post-Processing, choose Navlab. Give the pipeline a unique name. Enable this switch if you wish to have an email sent to you once the pipeline is finished processing. LiDARMill indicates the types of inputs required and the types of outputs that will be created. Click Next to move forward. Navlab can process multiple navigation files and reference stations at the same time. Here you can select Input Artifacts. You can click on the artifact or the switch on the right side of the time to mark the artifact as selected. Note that the red bars indicate when the data was collected. Ensure that your reference station file completely overlaps the mission data time duration. Once you've selected the files you'd like to use in processing, click Next. Under Processing Time Range, adjust the start and end times for processing your trajectory, if desired. The next step is to configure the rover. It is recommended to use the default parameters populated here. If you acquired data in the incorrect rover profile, however, you could correct for that by editing the parameters here. Note that the lever arm offsets are measured along the Novatel vehicle frame X vehicle right, Y vehicle forward, Z vehicle up. For the body to IMU rotation, rotate the vehicle frame into the IMU frame by rotating around the vehicle axes in ZXY order. Rotate around rotated axes for the second and third rotation. The next step is to configure the reference station position. Inputting the correct reference station position is a very important step in trajectory post-processing. Select from the available post-process positions in the drop-down menu, or enter your own custom position if you positioned your reference station over a known ground point. Configure the coordinate reference system of the known point using the wizard, followed by the horizontal and vertical coordinates of the known point. Make sure that you input the correct reference station antenna model, antenna height, and measure to antenna reference point. For this video, we will use the Opus Refined position. Note that refined Opus and RTX solutions require that observations were made at least 24 hours ago. For best results, input your reference station in the same datum as your project datum. By default, the output trajectory datum will match the LiDARMill project datum that was configured during project setup. Click Finish to begin processing the Navlab pipeline. LiDARMill processes your trajectory in the cloud, so you can navigate to another screen within the application, visit another website, or close your browser, and post-processing will continue in the background. LiDARMill will automatically send you an email when processing is complete if you selected that option when initiating the pipeline. While the pipeline is processing, you can check the progress of the pipeline under the Job Runs tab. Once the Navlab pipeline is finished successfully, view files and artifacts associated with the created pipeline under the General tab. When completed, the post-process trajectory and trajectory report will be located here. If you have any questions regarding the trajectory report, click on the blue I button for a link to our documentation portal where you can find detailed information about the trajectory report and much more. LiDARMill's spatial fuser pipeline uses the trajectory data generated by Navlab, combined with LiDAR and imagery data from your system, to generate a calibrated, classified, and colorized point cloud. Spatial fuser can also produce data products in the form of digital terrain models and digital surface models, contours, decimated point clouds, and more. It is possible to initiate a spatial fuser pipeline before the Navlab pipeline finishes processing. Simply select your Navlab trajectory when creating your pipeline, and LiDARMill will automatically start the spatial fuser pipeline when the Navlab pipeline has successfully finished processing. To begin processing your LiDAR data, create a spatial fuser pipeline by navigating to the Pipelines tab. Under Select Processing, choose Spatial Fuser. Enable this switch if you wish to have an email sent to you once the pipeline is finished processing. LiDARMill indicates the types of inputs required and the types of outputs that will be created. Click Next to move forward. Trajectory and LiDAR data are both required to initiate a spatial fuser pipeline. Fuser pipelines can also utilize camera data and ground control points if they are included within the project. Once you've enabled all the artifacts you wish to use for processing, click Next. Now it is time to configure the fuser pipeline parameters. First, specify the pipeline name and configure the dataset type, aerial or mobile, to optimize processing. Next, move on to configure LiDAR settings. By enabling the Use Full LiDAR Density switch, settings from the PLP will be overridden for achieving full LiDAR density. Disable this switch if you want to use settings that were previously defined in the uploaded PLP. For more information, check tooltips by hovering your cursor over the tool name, or click the question mark button next to the classification section to link to Phoenix LiDAR's detailed documentation. Configure the desired downward field of view, as well as the desired minimum and maximum LiDAR range from sensor to be included in the generated point cloud. Then move on to flight line configuration. There are two options for configuring flight lines that contain LiDAR data, which will be included in the generated point cloud. Option 1 is to have LiDARMill automatically split your trajectory into multiple intervals, each containing LiDAR data that was captured during straight flight lines. Automatic flight lines will be chosen based on the minimum time duration that you specify. Option 2 enables you to have more control over the flight lines. For this option, enable this switch and then click the Compute Trajectory Flight Lines button to specify which flight lines should be included in the generated point cloud. Specify flight line interval criteria and then click Compute Flight Lines. Note that you can reconfigure parameters and click Compute Flight Lines to recompute flight line intervals. The red lines indicate the intervals that will be used to generate the point cloud. The green lines indicate the active selected flight line. Disable the checkbox next to the flight line name to exclude undesirable intervals. Click Save at the bottom right to finalize selection. Move on to configure optimization parameters. In general, it is recommended to enable trajectory optimization on most datasets to improve the relative accuracy of the resulting point cloud. Trajectory optimization may not produce desirable results in cases where the dataset is exceptionally noisy, a large portion of the scanned area contains water bodies, or if the majority of the scanned area contains vegetation so thick that only an extremely low number of ground returns are present. In general, it is not recommended to enable sensor calibration unless a specific bore site calibration pattern was flown as part of the mission. When the sensor calibration switch is enabled, LiDARMill applies angular corrections to LiDAR sensor to resolve orientation misalignments from IMU to sensor. Depending on the LiDAR model, an additional ranging scale correction, tilt angle offset, or encoder calibration correction may be calculated and applied automatically. When the Enable Photos and Turn switch is enabled, photos acquired during turns will be utilized during point cloud colorization. Move on to configure classification parameters. Users can customize the ground classification routine applied to the resulting point cloud by editing the following parameters. Again, you can check tooltips by hovering your cursor over the parameter name, or click the question mark button next to the classification section to link to Phoenix LiDAR's detailed documentation. Enabling the AI classification switch leverages a neural network to infer point classification of 13 unique classifications. Move on to the LiDAR sensor lever arm and rotation configuration. Here it is recommended to use the default parameters populated. If you acquired data in the incorrect rover profile, however, you could correct for that by editing the parameters here. Move on to configure the camera sensor parameters. By enabling the Disable switch, camera data will not be used during processing. For the Override Settings section, it is recommended to use the default parameters populated here. If you acquire data in the incorrect rover profile, however, you could correct for that by editing the parameters here. If collected imagery has sufficient overlap and sidelap, 50% or more, it is recommended to enable Calibrate Camera. Camera calibration requires correctly setting initial focal length. For camera calibration to succeed, images need to contain mostly man-made features and little vegetation. It is recommended to keep per exposure pose correction enabled to optimize each individual photo's orientation to minimize errors between all photos. Move on to the final section to configure data product parameters. First, specify the output file name. When Tile the Point Cloud is enabled, this tool will automatically tile the output dataset into squares with a user-specified edge length or tile size. This is beneficial for large datasets. You can view and download tiled data by clicking on Select Tiles next to the Spatial Fuser pipeline once it has finished processing. The Cloud Clean tool fits a mathematical model of a surface to the original points of the point cloud, with the aim of representing the true surface as best as it can by excluding ranging noise. The three options include 1. Keep original cloud, which includes all points in the point cloud output. 2. Create smart decimated cloud where, given point density, the algorithm picks points that are nearest to a computed surface and then discards the points furthest away from the computed surface. And 3. Create smart projected cloud, which projects every original point to a computed surface and then keeps all the points from the cloud, but moves or projects points to the computed surface. Next is export data from curves. When enabled, this option includes data from turns within the generated point cloud. The turn data point source ID is set to 0. By enabling the Create Compressed Point Cloud switch, this option outputs the generated point cloud to a compressed LAZ 1.4 file instead of an uncompressed LAS file. Enable the GeoTIFF, DTM, DSM, CHM option to output various data products such as a digital terrain model using only ground classified points, a digital surface model using highest hit returns, and a canopy height model representing the vertical distance offsets from the ground model to the highest hit returns. The output GeoTIFF files have a user-specified resolution and are georeferenced to the configured LiDARMill project CRS. Finally, enable the contour switch to generate contours in the user-specified interval. Click Finish to initiate the pipeline. Under Job Runs, you can check the progress of the Spatial Fuser pipeline. Once the pipeline finishes processing, you can view files and artifacts associated with the created pipeline under its General tab. When completed, the LAS/LAZ files, as well as the project and processing reports, will be located here. If you tiled your data, use the Select Tiles button to download point cloud data. You can download an individual tile by clicking on it with the left mouse button, or you can select multiple tiles by holding down the Shift key and selecting an area by dragging the mouse. Alternatively, you can also navigate to the Deliverables tab to easily download all deliverable data products and point cloud tiles. The final step is to view, analyze, and share your processed data. LiDARMill allows you to quickly ensure your data meets required accuracy specs through robust automated report generation. A processing report for data processors and a project report for end users is automatically generated with each Spatial Fuser pipeline. End users can quickly and easily review detailed project information, including acquisition and processing dates, coordinate reference system information, deliverable product details, acquisition hardware information, mission survey altitude and flying speed statistics, reference station position information, trajectory details, relative and absolute accuracy reports, and various map types. Data processors benefit from the ability to review processing settings, system calibration details, point cloud statistics, and much more. If you have any questions regarding the processing and project reports, click on the blue information button for a link to our documentation portal where you can find detailed information about each report section. Upon completing a Spatial Fuser pipeline, LiDARMill prepares a 3D point cloud for user-friendly viewing in a cloud viewer. View your point cloud by clicking the Open Cloud Viewer button on your Spatial Fuser pipeline. LiDARMill's Cloud Viewer makes it easy to share point clouds with anyone. It's as easy as copying the URL and sending it to whomever wishes to view it. The end user does not need a LiDARMill account to view and interact with the point cloud as demonstrated in this video. From this interface, you can navigate through your data. Click this button to open more analytics tools. Under the Appearance tab, customize various parameters related to the point cloud viewer. You can adjust the number of points displayed, change units, enable eye-dome lighting, and more. Under the Tools tab, you can leverage LiDAR's accuracy by making measurements using a variety of tools. One of the most useful tools is the bounding box used to create cross-sections or profiles within the point cloud. Select the tool, left-click the start of the profile, left-click the end of the profile, move your mouse to adjust the depth, then left-click to finalize the selection. Under the Scene tab, you can adjust the profile depth and click the Show 2D Profile button to view your selection. Make measurements using the measurement triangle. Here you can also enable and disable viewing of control points, trajectories, the DTM, individual flight lines, and more. Use the Material tab to change the way you view your point cloud. Color by elevation, color, flight paths during acquisition, intensity of laser pulse returns, and classification, to name a few. Use the Classification Filter tab to toggle on and off all items of a specific point class. Under the Fly tab, you can quickly and easily create fly-throughs of your processed data. Use the Snapshot tab to quickly and easily create downloadable data snapshots. To access more detailed documentation, log into our website and navigate to Client Links, then User Manuals, and click on Phoenix LiDAR System's Comprehensive User Manual and scroll down to LiDARMill Cloud Processing. It's been a pleasure walking you through the LiDARMill workflow from start to finish. Thank you for watching. This is Kory, signing off.